Hello. In my last video, I talked about FlightAware.com and how you could use it to get real live data from airlines in a somewhat indirect sort of way. You can read the FAQ on FlightAware.com to see where they get their data and how they generate it. And just to recap, these are all of the flights that are currently in the air around the world. You can pick a flight by clicking on any one of these airplanes, and that will take you to a separate page like this one. And if you turn on the debugger, you can see that this page makes a request to trackpoll.rvt. I've already shown how all of this works. And from there, you can go copy as a curl command, and the curl utility allows you to add it to a script, for example, and to run it multiple times so that you can track the flight in the air. I just loaded this URL in a separate tab like this, and the hierarchy of this JSON file has an element called track. Inside this track has a number of objects, and each one contains a timestamp, the longitude, the latitude, the altitude that the airplane was at that time, along with its ground speed. So I took my parse script that I had previously written and I modified it to go and extract the tracks out of the data. And after it output the values that it had output before, I want to guarantee that each of these is in the correct sequence. I key in on the timestamp, and then I sort this map on the keys, which should be the timestamp. And so I'm able to generate a sorted index. After that, I go through this sorted index, starting at the second element, not the first. And then I compare the time elapsed between that one and the previous one so that it gives me a total number of seconds that have elapsed between these two coordinates. I pull out a few other things. The spreadsheet that I had created uses the distance traveled, not the ground speed. So I had to recalculate the distance based on the ground speed and the total seconds elapsed. I output a separate line for each track point. And so each line represents a line segment between 2 points. So the output will always be one less than the number of tracks. So the first segment is going to be between the first and the second. The second track is going to be between the second and the third, and so on all the way to the end. As I'm building this, I'm also building KML coordinates that I can then import into Google Earth, and you'll see that in a minute. I have a KML template that I substitute a few values. Then I output the route-specific KML file that includes all of these track points in something else that I used to compare on a flat Earth. I'm going to parse it out. And as you can see, the output is basically a series of data points that are similar to the last one. To spare you some time, I've already done this on a few flights already. This is one of the ones that I had already done for the last video. This one is between Dubai and Sydney, and I've got another one between Santiago and Miami. If we look on the difference in kilometers between what I computed from those geocoordinates and what FlightAware provided based on the time between the 2 points and the ground speed to recompute the distance between those 2 points, you can see that they are very close together. This one is within 9.5 meters between calculated and provided. This one is about 4 meters between calculated and provided. Some of these were not provided at all. And there are a few that are slightly higher than the average. This one is almost half a kilometer difference. If I compare the same thing with the flat Earth, however, some of these values, like this group, in fact, most of these here, the difference between the ground speed and the time that FlightAware provided versus what I calculated what it should have been on the flat Earth, the difference in the distance in this case are measured measured in multiples of kilometers. I also wanted to see how it would look on a flat Earth. So the first thing I did as a very simple test was to create a scatter plot that should represent what the bird's eye view should look on a flat Earth. So I created a scatter plot of columns AC and AD. Those represent the X and the Y coordinates of the origin geocoordinates for that line. The X-axis on the graph would represent the X coordinate. The Y-axis on the graph would represent the Y coordinate. I chose 4,000 kilometers for the data range for both the X and the Y, and I also change the aspect ratio so that they are more or less squares like that. And as you can see, this represents the route that was actually taken, and it appears to be slightly curved on a flat Earth, when the shortest route between the 2 points would have been more where this trend line is. Now this trend line should really be shifted up to here, but you kind of get the idea. So that got me thinking a little bit further, and that's where the KML data comes in. So I had done this before I got the script to output the KML data, running the script on those flights that I had already extracted. I was then able to load each of the KML files into Google Earth. The red line is what Google Earth has calculated as the Great Circle route distance between the origin and the destination. The purple line that you see consists of all of the waypoints along the flight that have taken place. So these are all of the geocoordinates that the plane has reported of its location. And so here is the Florida to Miami route. Here's the Florida to Argentina route. If we rotate the Earth so that it's a straight line, you can see that the purple route follows along reasonably closely. And I guess there would be reasons why they would detour. In some cases, there may be a military exercise in a no-fly zone. Maybe there's a thunderstorm. Maybe they're just doing this to make it easier to turn around and line up to land at the airport, at the destination. There are multiple reasons I can think of. But you can see, no matter which flight I take, on a globe Earth, these flights here, this one in particular, you can see the flight didn't get very far. It left Toronto and it was headed towards, looks like somewhere in China, I think. And so it was still over Canada at the time that I took that flight. But straight line, straight line, straight line, straight line, straight line, straight line, you get the idea. This one is a fairly straight line. Now I'm looking at the purple lines. Apart from a few deviations, these are fairly straight lines, so on and so forth. If I compare that with the flat Earth, this is the output of the extra CSV file that I had created. The purple line that you see is where the airplane reported its position in mid-flight. The white line that you see is where I recompute the Great Circle route between those two coordinates for a globe Earth. And that white line would be the same as this red line. The yellow line represents the shortest distance it would be if the Earth was flat. Some flights, like Toronto to China, have the globe Earth, flat Earth, and reported flight paths all matching a similar route. You can see this one is somewhat similar. White line represents the globe Earth Great Circle route. Purple line represents where the flight really went, and the yellow line represents the shortest path that it would appear on a flat Earth. And as for this one, this is what the flight really looked like on a globe Earth, for example. So it's always possible that there might have been some kind of conflict going on here that they decided to take this alternate route. But while it may appear like some routes fit for both globe and flat, there are many flights that appear to be completely different and only work if the Earth was a globe. If we look at this flight, for example, this is from Chile to Argentina. That would have been this flight. The reported distance, or the Great Circle route distance, was 616 nautical miles. I had calculated 614 nautical miles using the Haversine function to calculate the point between those two geocoordinates. The flat Earth distance would have been 1,593 nautical miles for a difference of 977 or 1,811 kilometers difference. It would be easy enough to see why on a globe Earth. The equator, which is the greatest distance between any 2 points of longitude, is right about here. Argentina is very much farther south of the equator, and so for the same distance between 2 points of longitude, the distance that you can measure with a tape measure is much less than it would be at the equator. So in other words, at the equator, for the same given distance between 2 points of longitude must be the greatest distance on a globe. Any point north or south of that would be less than that. However, on a flat Earth, because these 2 points are further from the center of the flat Earth, by necessity, the distance between those two geocoordinates, between those 2 points of longitude, must be even greater than the distance between those two same points of longitude at the equator. So we get a multiplication factor of error. The further south you go, the greater the distance difference between the globe Earth model and the flat Earth model. And that would be the reason why this one has over 1,000 kilometers, almost 2,000 kilometers difference between what the globe Earth calculated and what the airline provided. Once again, this is yet even more evidence of the same proof that if you look at airlines and if you look at flights in the real world, every metric you can think of, whether it's flight speed, whether it's distance between the airports, whether it's the routes taken, every metric you can think of lines up with the globe Earth, and they do not line up with the flat Earth. Anybody would have to come to the conclusion, therefore, that the Earth must be a globe and it cannot be flat. And yet here we are continuing this never-ending discussion between globe Earthers and flat Earthers. If you like this video, I would appreciate the thumbs up, the subscribe, leave a comment below. You know what else to do. Thank you for watching, and I'm going to see you again in another video soon enough. So bye for now.